Welcome to part 2 on the implementation of a simplified DLX. Let's recall what the data path of the simplified DLX looks like. The data path is basically the part that appears over here. This is the data path. The data path is connected to the memory controller in 2 locations, and it is also connected to the DLX controller, which is not depicted over here, and we discussed the different signals that are sent from the controller to the data path and from the data path to the controller, so I won't elaborate on them now. I want to start with the ALU. The ALU environment is a combinational circuit that supports addition and subtraction, bitwise logical instructions, and comparison. You could think of it as a box that has 2 inputs, X and Y. These are the 2 operands. An output Z, this is the outcome of the ALU, and 5 bits which encode the operation or the computation that the ALU needs to perform. Inside, the ALU consists of 3 parts: the adder subtractor, bitwise XOR, bitwise OR, bitwise AND, and a 32-bit comparator. The ALU is a combinational circuit. As I said before, it has 2 inputs, X and Y. These are the operands, or the arguments, or operands. And we have 5 bits, which is the type. This is an encoding of the function that the ALU environment implements. The output is called Z, and it is simply the value of the function, which is encoded by the 5 bits of the type, applied to the 2 operands X and Y. Let's discuss how the different functions are encoded. We have 5 bits of the type, and the function that is encoded by these 5 bits appears over here. The choice of the encoding is such that it's supposed to assist in the implementation of the ALU. I will not elaborate on the exact choice of Y, X less than comparison between X and Y, checking whether X is less than Y is encoded as 10010. There are reasons for it, but I will not elaborate on them. They have to do with the simplification of the implementation of the ALU. I want to emphasize that whenever the function is a comparison, then the output is either a 0 or a 1, depending on whether the expression is true or not. Logical operations are bitwise operations. The comparison operations, as I said before, return a 0, namely the string of all zeros, or a 1, namely the string of 31 zeros followed by 1. The type 0 input, this is the bit that you see over here. See, this is this column. The type 0 input indicates if the function that is actually being performed is addition. It is used, for example, if you want to increment the program counter, because the ALU is also in charge of computing PC gets the value of PC plus 1. This is the increment of the PC. The input bit type 1 indicates if the operation is a comparison. So if you look at this thing, then whenever it's a 1, then we have a comparison. The ALU is connected to the data path. It's better depicted, so let me explain this by the depiction. So in this depiction, this is the ALU, and we see that it is fed by 2 buses, S1 and S2, where S1 is the output of the S1 mux, and S2 is the output of the S2 mux. The ALU environment has an output. The output is connected to the Z2 bus, which feeds this mux. In addition, the ALU environment is fed by the DLX controller, which sends it the 5 bits that encode the function that it needs to evaluate. Okay, so we understand everything that we need regarding the ALU environment. The shifter environment, let's see it in the data path. So that here it is. This is the shifter. Well, let's describe the shifter. The shifter is a 32-bit bidirectional logical shifter by one position at most. So it can either shift one position to the left, one position to the right, or not at all. We denote LLSXI. We denote by LLSXI the logical left shift of X by I positions, and similarly LRS is the logical right shift of X by I positions. So what the shifter does is it has an input X, a single bit which indicates whether a shift should take place, a single bit that indicates whether the shift is to the right. The output is again 32 bits, and Y is either X if no shift takes place. It's a logical shift of X by one position to the left if shift is 1 and right is 0. It's a logical shift by one position to the right of X if shift is 1 and right is 1. So you notice that when shift is 0, the output simply equals the input, namely the shifter implements the identity function, and this will help us in routing information around the data path. Now let's talk about the instruction register environment. Let's find it in the data path, so let's make sure we know where it is. Now we're talking about this part, the IR. The instruction register environment holds the 32 bits of the current instruction that are fetched from the memory. When you execute an I-type instruction, the IR environment outputs the sign extension of the immediate field and the indices of RS1 and RD. When you're executing an R-type instruction, the IR environment outputs the indices of RS1, RS2, and RD, all of which are fields inside the instruction itself. Now notice that the RD field is positioned in different places in I-type and R-type instructions. So selecting the right bits requires a circuit that computes whether the instruction is an I-type instruction or not. We delegate this task to the DLX control. So the DLX control receives the instruction and tells the IR environment whether it is an I-type or R-type instruction, and therefore that will tell it where the RD resides. Okay, we use a special signal for that, which is called I-type. So the formal specification of the IR environment, it's a synchronous circuit. It has a data input, a clock enable for its register, a signal indicating whether it is a jump link instruction, whether it's an I-type instruction, and of course the clock. The output is the encoding of the instruction itself, 32 bits, which are sent to the control. The sign extension of the immediate constant in case it's an an I-type instruction, and of course the GPR addresses A, B, and C, 5 bits each, which corresponds to the fields RS1, RS2, and RD. The functionality: if you have a clock enabled, then you sample the DI and that becomes your next instruction. Otherwise, you keep the old instruction. You take the 16 least significant bits of the instruction. You perform a sign extension to them, and that will be your constant, the immediate. Of course, this will be true only if the instruction is an I-type, but if it isn't an I-type, then this thing is just gibberish and we shouldn't worry about it. The A address is, of course, the encoding of RS1, which is always in this location of the instruction. The B address is an encoding of RS2, which is always in this location. Of course, if the instruction is not in R-type and there is no RST, and therefore this B will not be very interesting, but it's not going to create an error. and this will be the destination register. And we have three cases. We have one case where the instruction is in R type, so then RD resides over here. The other type case is when it's not an I type, and then the RD resides over here. And the third case, which is the most interesting case, is the case in which we're performing a jump and link instruction, and then we recall that we want to store the incremented PC in R31. So just recall that this thing encodes 31. So we want the destination register, R31, to be used as a place to store the incremented PC. So therefore the CADR will equal 31. Okay, you implement the IR environment by a parallel load clock-enabled register, and you need some muxes to select the right value of the CADR. Let's see how the IR is connected to the data path, better shown on the figure. So this is the IR environment. The instruction is fed from the memory, so it comes through the data in bus into the IR environment. The immediate is output through here, goes into the S2 mux. The controller is given by the IR the current instruction, and it sends back the flags that tell the IR environment whether the instruction is a J-type, J-link instructions, and whether the IR register should be updated, namely it needs a clock enable. In addition, the IR environment sends addresses of 3 general purpose registers to the GPR. These are 5 bits each. So each of them is 5 bits because you want to encode an index between 0 and 31. This is the AADR, the BADR, and the CADR that of course correspond to RS1, RS2, and RD for the GPR environment. That completes the description of the IR environment. In addition, we have the PC environment, it resides over here. The PC environment is very simple. It is simply a 32-bit clock-enabled parallel load register that stores the program counter. So there's no extra circuitry in the PC environment. Now let's elaborate on the GPR environment, which we have also discussed in part 1. This is this fellow. We have 32 registers, general purpose registers in the GPR environment. They're called R0 to R31. The GPR environment can support one of 2 operations in each clock cycle, either write the value of the input C in the register Ri, where I is the index that is encoded in binary by the CADR input, or you could read the contents of Ri and Rj, where I is encoded by AADR and J is encoded by BADR. The GPR is a synchronous circuit. The specification is as follows. It has inputs. These inputs are 3 addresses, AADR, BADR, CADR, each of which is 5 bits long. These encode indices between 0 and 31. We have the data input C, which is 32 bits long, a write enable signal, which tells us whether we are performing a write to the GPR, and of course the clock signal. The outputs are A and B. We already saw these in part 1, 32 bits each, and a flag that indicates whether A equals 0. Okay, let's describe the functionality. Let Ri denote the register whose index is I in the GPR, and the functionality is specified as follows. We think of the GPR as storing an array of 32 words, each of which is 32 bits wide. We initialize by setting zeros in all the general purpose registers, and then we run this loop forever. If we're performing a write and the CADR is not 0, because we cannot change the value of R0. Recall, R0 always equals 0. So you cannot write anything to R0 because it has to stay 0. So if the address CADR is not equal to 0, so you take the register whose index is CADR and you store the value of C in this register so that in the next clock cycle this will be the value of this register. This is the case of a write. In the case of a read, for reading from the GPR, the GPR WE is 0. And then what you do is you take these two addresses, AADR and BADR. These are numbers between 0 and 31. You access the corresponding registers, and you copy the contents of this register to A and this register to B. The A equals 0 simply tells us if the output of the A register is the all zeros string. We're not mentioning here all the registers, only the registers with clock enables which are 1. The other registers were, the general purpose registers which are not indexed by AADR, BADR, or CADR are not mentioned in this slide. Notice that AADR may equal BADR; they don't need to be distinct, and therefore you might be reading the same register twice into A and B. That's no problem. I just want to emphasize that this is a little bit sloppy because this signal, the A equals 0, refers to the output of the A register, not the input of the A register. And actually the A register is not part of the GPR. It's outside the GPR. Okay, so now you may ask yourself, how do I implement this functionality of the GPR? In fact, the GPR is a dual port RAM. Dual port meaning that it could perform two reads simultaneously. That's the dual, the two things. This is this too. So you can read two registers at once in one clock cycle, or you can perform one write. You could implement this dual port RAM by a special RAM with two decoders. I'm not going to elaborate on that. We suggest a brute force design in which we just use two separate RAMs. So this would be the first RAM, this would be the second RAM, each of which is 32-bit words. 32-bit words are stored in each of these RAMs. And the contents of these RAMs, the invariant is that the contents of these RAMs is always identical. So this is the invariant. Both RAMs store the same contents. Okay, so this is our invariant. Initially, these RAMs are initialized to 0. And now this is the C input, this is the input to the A register, input to the B register. Now we either perform a read or a write. Let's start with the case of a write. So in the case of the write, we have our GPR write enable, and let's try to first send it naively to the both inputs of these RAMs, to the read not write inputs of the RAM. And what would happen if we would do that? Suppose we were to invert it so that it would work correctly, then we would be writing into the RAM. What would we be writing? We'd be writing this C. In which address? In the address which is given by the CADR, because this GPR WE would be 1, we would select this input, and the C would come into here, and in addition, the C would go like this, and it would come into here. This would be the C, the address of the C, and we would copy this thing into the general purpose register. This is the index of it, and we're happy. What is the problem? The problem is that we're not allowed to write into R0, right? So we have to check whether GPRWE, whether CADR is all zeros. And if it is all zeros, then we are in a bad case, because then we don't want to perform the write. Okay? So what this circuitry does is it cancel the right if CADR is all zeros. Okay? You want to cancel the right if this address is the all zeros, because you're not allowed to write to R0. It's supposed to stay constant 0. Okay, so that explains this part. This is a strange part. Now, if indeed the CADR is not all zeros, then this OR tree outputs a 1, and what we have here is the NAND. So GPR WE prime is the NAND of GPR WE comma 1, because if this is not all zeros, then this will be a 1. Okay, good. What does this do? This simply gives us the NOT of GPR WE. Okay, so the write enable becomes a not write enable, and this is okay, because this is exactly the signal that you want to feed into the RAM. You want to tell it whether it's a read, not whether it's a write, but whether it's a read. Therefore, you need to negate the bit. Okay, that's completes the discussion of the write operation. Let's talk about the read operation. In the read operation, this fellow will be a 1. Okay, so if we have, let's change colors. So in a read, this will be 1 and this will be 1, telling us we want to do a read. The GPR WE would be 0, this will be 0. This means that we choose this path and we choose this path. So here we will have the AADL, and here we will have the BADL. Okay, so from the first RAM, we're reading the register whose index is AADR. From the second RAM, we're reading the register whose index is BADR. Now recall, the invariant tells us that both RAMs store the same contents, because whenever we perform a write, we do the same write in both of them. So this invariant is indeed maintained. Now we are reading the register whose index is AADR from the first RAM. We're reading the contents of the register whose index is BADR from the second RAM, and we will get this output and we will get this output. So this will feed the B register, this will feed the A register. And this is how the read takes place. And the equality with 0, we take the output of the A register, we feed it into a 0 tester, and that will be our A equals 0 signal. Good, so we understand the implementation of the GPR, and in the next part we will talk about how to implement the DLX control.